Good morning, everyone. So we'll continue with chapter 2, and the plan is we'll complete chapter 2 today, and we'll have our first test on Thursday based on chapters 1 and 2. So last time we talked about numerical measures of location, like mean, median, mode, quantiles, and so on. One disadvantage or one shortcoming of numerical measures for location is that it only gives you part of the information. It doesn't give you full story. If somebody's head is in oven and legs in a freezer, average will be normal, but obviously that person will not feel comfortable. So mean will tell some part of the story. We need to assess variability in the data to get a complete picture. As I mentioned earlier, like when you look at a histogram, you have to look for location, spread, patterns. Same thing here with numbers. We did location, and now we talk about spread or variability. And most common measure of variability is range, maximum minus minimum. You take the difference of whatever maximum you have in your data and minimum, you get a range. So very simple. It depends only on two values, maximum and minimum. It doesn't care what happens in between. There is another measure of variability. It's called interquartile range, which is Q3 minus Q1. So it looks at middle 50% of the values. As you know, Q3 is something where you are in third quarter, so 75% is over, 25% remaining. And Q1 is first quarter, 25% over, 75% remaining. So in between 50%, what is the range? Why it is useful? Why not like only range? So range depends on maximum and minimum. Now those values are very variable. So you collect data again, your maximum may be very different, and suddenly your range becomes a very different number. So if you have especially like skewed data, left skewed, right skewed, or data set which is not symmetric, interquartile range will be more stable. You calculate Q3, calculate Q1, third quartile and first quartile, and take the difference. So that range will not change much. So that is called interquartile range. It can be used for finding outliers. If you have this data, some measurement, and if you find two values, one is first quartile minus 1.5 times IQR, interquartile range. Similarly, if you calculate Q3 plus 1.5 times the interquartile range, anything below this and anything above this is outlier, like likely outlier. Outlier is a value which doesn't belong to the group, or there could be like some error, for example. If we buy a car and a company like, let's say, Ford, it collects data after like whatever repair is done. So if they find there is a car which has been driven only maybe 10 miles in 10 months, it is very likely that somebody, when entering the data, made a mistake. So while typing, maybe some zeros were left or some digits were left, because why somebody will buy a car and keep it for 10 months and only drive 10 miles? It could happen, but it is a likely outlier. It is a very unlikely number. So those kind of values may fall outside. It could be typo, somebody entering data, or it could be something very strange. So you can figure that out using interquartile range. You subtract from first quartile 1.5 IQR and add to third quartile 1.5 IQR. So if the values are greater than this or less than that, so that's an indication that those values are suspicious at least. Or it could be something very rare event, like, so we had data on number of steps walked, and the data points were like 1,000 to 21,000. And if we have a data point which is like 100,000 steps, so it is not impossible, but it is likely that somebody put a, by mistake, extra zero, like while typing. So it could be a typo. It was 10,000, but by mistake, somebody entered 100,000. This can be used for calculating whether we have outliers. The most popular method for capturing variability is called standard deviation. So this is the method for capturing variability which has become standard in the world. That's why it is called standard deviation. Anybody who wants to assess variability, how much variability exists in the data, they use standard deviation. It's just like a thermometer. Like if you want to measure temperature, you use a tool and find out whether temperature is high or low. Same way, you can use standard deviation to find whether the variability is high or low. Suppose I have data on Tesla stock price for last 3 days, and they look like this, something like this, 250 on one day, next day 245, next day 255. Obviously, there is a variability in the data. All the data points are not exactly same. So there is a variability in the data. So how can we calculate standard deviation? What we do is, let's call this variable x. We first calculate average or mean. So mean is still needed. So if you add all the 3, divide by 3, you should get 250. Now x minus x bar whole square. What is x minus x bar? Deviation. How far this number is from the mean. So within parentheses you have how much deviation. But then we square it. We square the deviation. 250 minus the average whole square is 0. So how much first number deviates from the average? There's no deviation. 250 exactly at the same place. So deviation is 0, square it, it is still 0. 245 minus 250. So this number deviates by 5 on the lower side, and then we square it. So 5 square is 25. This is on the higher side, 255. Square it, you get 25. We add them, we get 50. So how much is standard deviation? Let me represent this by small s. So standard deviation is given by square root of this 50 that we got and sample size minus 1. So sample size minus 1, so which is 50 divided by, so n is 3. We have 3 data points, so 3 minus 1. So 50 divided by 2 is 25, and square root of 25 is 5. And dollars. So this is like, because units of original data is in dollars, so standard deviation also is in dollars. We squared the deviations that would have made the units like dollar square. So when we take this square root again, we bring it back from dollar square to dollars. So units of standard deviation is same as the original units. So if your original data is in millimeters, standard deviation will be in millimeters. So standard deviation equals square root of x minus x bar whole square that we did. And for adding everything, we use a symbol like this and dividing this by n minus 1, sample size minus 1. So that gives us the formula for standard deviation. Now if your, let's say, data points are 250, 250, and 250. What will be your standard deviation if you apply the same process? Yeah. So 250 minus 250 whole square is 0. 250 minus 250 whole square is 0. So you add everything, you get 0. 0 you divide by whatever, it is 0. You take square root of 0 will be 0. So standard deviation is 0. So when there is no variability in the data, it tells you that the variability is 0. Can it be negative? Can this value be minus something, minus 5, minus 3? Can it have a negative value? Not possible, right? Because of this square. Any deviation you take, like 245 minus 250 is negative 5, but as soon as we take a square, that negative goes away. So it cannot be negative. So one property of standard deviation is S is always greater than or equal to 0. Minimum possible value is 0. It cannot be below 0. And you'll get 0 when all the values are same. What if I have this data point? I have a variable x and I have one sample. What will be your standard deviation? If you apply the same formula or same process, how much do you get for standard deviation with just one value, one sample size? Let's go through the steps. So first you find the average. Average is 250. So you have only one value. There's only one location. So average is 250. Now calculate deviations. 250 minus 250 whole square. What you get is 0, right? So S equals 0 divided by n minus 1. How much is n minus 1? Sample size is 1, so n minus 1 is also 0. What is 0 divided by 0? Undefined. In mathematics, you may have studied somewhere. It is not defined. You cannot divide 0 by 0 or any number by 0. So this is not defined. Not defined means you cannot calculate variability in the data when you have only one data point. Sometimes, like, people forget that. I remember I was consulting to a big auto company in some other country. And we had one meeting with a very senior manager. And they used to do testing of one of the parts. And managers always try to find out if we can reduce the cost or time, get it done early. So he asked a very innocent question. Can we reduce the sample size to just 1? Because it takes a lot of time to run like 3 or 5 samples. Can we estimate the variability using sample size of 1? So we had to show him this formula that you cannot calculate variability if you have only one data point. It is not possible. It is not defined. You need minimum 2. Sample size has to be greater than 1 for this standard deviation to be valid. Just like any instrument or product, they work in a given condition, not every condition. Similarly, this tool for assessing variability will work in some conditions, which is like at least you need more than one sample size. If you have less than one sample size, then forget it. Standard deviation for population, if you recall first chapter and sample, we use sigma, this Greek alphabet. Whenever we are talking about population, usually we write their properties using Greek alphabets, like this is called sigma. And sample we can just use small letter s. You might have seen on calculators, another measure related to variability is your z-score, which is equal to x minus x bar divided by s. So it makes use of both mean and standard deviation and calculates a z-value. So for this one, let's look at one example. 116. Elementary school class ran 1 mile with mean 11 minutes and standard deviation 3 minutes. So let me first write down what is available to us. Elementary school and x bar and standard deviation. So 11 minutes and 3 minutes. And then a student in the class ran 1 mile in 8 minutes. So this student took 8 minutes for a mile. Now we have junior high school, where mean is 9, standard deviation 2. And then there is a student from that school, Kenji, who ran 1 mile in 8.5 minutes. And finally we have high school, mean 7 minutes, standard deviation 4. And a student from high school, Nedda, 8 minutes. So question is, why is Kenji considered better runner than Nedda? So that is part A. Clearly, Kenji took more time, 8.5, but Nedda took only 8 minutes. So 8 minutes is better than 8.5 minutes. But question is why Kenji is considered better runner than Nedda, even though Nedda ran faster. That's where z-score comes into picture. So these numbers are not comparable actually. If you only look at 8, it looks better. But look at like how high school students run. They take on an average like 7 minutes with a standard deviation of 4. Whereas junior high school, they take 9 minutes more time and less standard deviation, and maximum time is taken by elementary school because they are much younger. So those numbers are not comparable directly, but if we convert those numbers into z-score, then we can compare. So z-score basically allows you to have like apple to apple comparison. So how do we calculate z-score? Z for elementary school, formula is x minus x bar by s. So x is 8 minus 11 divided by 3. For Kenji, it is 8.5 minus 9 divided by 2. And for Nedda, it is 8 minus 7 divided by 4. So how much is this? So 8 minus 11 is negative 3. So 3 by 3 is 1. So first number is negative 1. 8.5 minus 9 is negative 0.5. So negative 0.5 divided by 2. So negative 0.25. 8 minus 7 is 1. 1 divided by 4 is 0.25. So now we have z-scores for each one. So question was, why is Kenji considered better than Nedda? So why this negative 0.25 is better than 0.25? Now it makes sense. So lower values of z means they are running faster compared to their group. So within junior high school, whatever time they take in terms of mean and standard deviation, anything less than 0 is better than average, and anything more than that is worse than the average. So obviously Kenji is doing better here because z value is less. Another method or calculation we use is Chebyshev's rule. So this is called Chebyshev's rule. that this much of items in any data set. When they talk about any, it means any data set in the world. So what it means is, let's say if z equals 2, if you have a situation where z is 2, then you calculate at least 1 minus 1 by z square. So 1 minus 1 by z square is 1 by 2 square. So 1 minus 1 by 4. So this is 3 by 4 or 75%. So at least 75% of the items in any data set are within 2 standard deviations of the mean. So whether your distribution is like symmetric, skewed, left skewed, right skewed, bimodal, irregular, whatever may be the shape of your distribution, you know that at least 75% is within 2 standard deviation. If you go to 3 standard deviation with z equals 3 and do the same calculation, so 1 minus 1 by 3 square, so 1 minus 1 by 9, which is 8 by 9, which is roughly 88.9%. So from average, if you walk 3 standard deviations to the right, 3 standard deviation to the left, that will include 88.9% of the data, whatever may be the shape of your distribution. In terms of z, the middle, 1, 2, 3. 1, 2, 3. So 3 is somewhere here. Your data may be skewed like this slightly, or whatever may be the case. In between these two, you have 88.9% of the values. Now compared to this, there is another rule. It's called empirical rule. So empirical rule is mainly for symmetric distributions. So if your distribution has a shape like this, so obviously your average is in the middle, and if you go x bar plus standard deviation, x bar plus 2 standard deviation, x bar plus 3 standard deviation, on the left side x bar minus s, x bar minus 2s, x bar minus 3s. Let me try again. Something like this. Then within plus minus 1 standard deviation, like total data points will be roughly 68%. Within plus minus 2 standard deviations, 95%. And within 3 standard deviations, 99%. So if the shape is symmetric, maximum possible percentage is 99%. If the shapes are not symmetric, irregular, then at least 88.9%. That's plus minus 3 standard deviation. So within plus minus 3 standard deviation, these two put together give you a range, at least 88.9, and it can go as high as 99. So if your histogram is symmetric, you can go up to 99%. So these are like 2 extreme limits. Another measure that combines mean and standard deviation is called coefficient of variation, CV. So CV is given as standard deviation divided by mean times 100. So that's the formula. We'll do some calculations. Type Posit Cloud. Click on the first thing that you see. It says Posit Cloud. So go there and it will automatically log you in if you created account last time. If once you are here, you will not see so many things. You will only see what you did in the last class. I did that last time. I think this is the one. And if you recall, we worked on chapter 2. I named that file as chapter 2, so that file is here. And it automatically opens for me. So everything is saved here, and we continue below. So I had saved this file as chapter number 2. Last time I showed you like you can put data and then create histograms and summary and all that very easily. Let's say I'm interested in finding how Tesla and let's say Ford, they did this year so far in the stock market, how their prices changed, and also calculate coefficient of variation to figure out relative variability, like which one was more variable. One thing I did not show you last time, I'm going to introduce right now. So there are so many companies, so many experts who write packages for this program. So you have like packages from Facebook, Google, and so many other companies. Now to use those packages, we have to first install a library. Just like if you want to read a book from the library, that book has to be ordered, so it will come in the library, and then you have to check out to get that book and read. So to order that book so that it becomes available, we install the package. So I'm going to install a package by going to the fourth window. It says packages, and then install. So the name of this package is QUANTMO. So as I type, I see there's only one option left, so that's the one. And this is all lowercase, no uppercase, and then I say install. So now it is ordering that book so that it comes to the library. And once it is done, that means now book is available. But now I have to go to the library and get the book. So for that, we type library. So as you type library, first one, and what do you want? So I have to say that Quantmod. So click on that, and then you have to run that line. You have to run that line. You can run using this line at the top, or there's another way. You can hit Command Enter on Apple and Control Enter on Windows. So now this library is available to me. So what I want to do is, I want to get some data on symbols. So get symbol. So when you say get symbol or symbols, select this one and then let it know that you want Tesla, TSLA. So that's the symbol for Tesla. Now what data do you want? From where to where? Because there are tons of data available. So I want this from like only this year, so 2024, and I can say 1st of January, and 2. So for 2 I can say 2024, and we are in September. The markets are not open yet. Today is 24th, right? So let's say 23rd. So you want that data, you run this line, and that data will be available. Now how this data looks, if you simply want to do chart, so there is an option called chartSeries, and if you say TSLA, so if I run this line, you will get this plot. This is just a time series plot where Tesla was at the beginning. It went down, it went up, and there is a variability in the data. Now, if I do the same thing with the Ford also is an auto company. So I'm going to keep the dates but change ticker symbol to F. For Ford it is just F. And run this line. And this is F. So it also varies. Now I don't know if you noticed, Ford varies around like maybe $9 to $15. But if I go back and look at Tesla chart, it varies from 140 to 260 or 270. So in terms of absolute numbers, you are looking at two very different situations. A stock that trades from 140 to almost 300, so 3 digits, and Ford you have like single digit or maybe 2 digits. So very different values for the two companies. Now if you find average, you get those values, but you cannot directly compare variability because the numbers are so different. And that's where coefficient of variation comes into picture. So you can, if you want to compare which one is more variable compared to the values it has, you can make use of coefficient of variation. If I say Tesla, like what data do I have? I just want to look at some data like in terms of for Tesla. So it has all these values. On this date, what was the open price, what was the highest value, what was the lowest, close, volume, and so on. The most important number here is close, where it closed on the day. Where did Tesla close on that given day? So January 2nd, because first may be a holiday, January 2nd, it closed at $248.42. We'll just use the close for Tesla as well as Ford and find average and standard deviation first, because that's what we need for coefficient of variation. So for Tesla, mean. So how do I find out of all the values this close value? So we have to say Tesla, where our data is, and then put a $sign, so it will list all the columns in the data. Then I choose close and run. So Tesla had an average of $197.72 this year so far. If you want to find standard deviation, same thing, TSLA, and then put a $sign and choose close. So SD for standard deviation. When you run this, so $26.89 of standard deviation for Tesla. Now let's do this for Ford. Mean for F. So Ford, remember it's case sensitive. I cannot put lowercase f. If I have used uppercase f, it has to be uppercase. So for Ford close, and the mean is $12.01. Standard deviation F $0.98 98 cents standard deviation. So very different. Obviously the scales are very different. So things are not directly comparable. So now let's calculate the coefficient of variation using the formula that I gave you. So S divided by mean. So I will call this, I'll just put an arrow and save mean in M. Similarly, I'll put an arrow and save standard deviation in S. So now, if I calculate standard deviation divided by x bar, so S divided by m. We should also multiply this by 100. So I will also put a comment, like remember hash symbol. So this is CV for Tesla. So this is just a comment. So whatever we calculate is the CV. So 13.6. We do a same thing for, let's call this M1 and run S1 and run. And then we do 100 times standard deviation is S1 divided by M1. And this is CV for Ford. So Tesla has a CV of 13.6, Ford has a CV of 8.16. So Tesla has a higher coefficient of variation. Standard deviation is 13.6% of the mean for Tesla, and here standard deviation is 8.16% of the mean for Ford. So Tesla is exhibiting much more variability compared to Ford. Let's do one example. So this is example 123. 25 randomly selected students were asked number of movies they watched previous week, and this is the data. 0 movies, 1, 2 up to 4, and then you have frequencies. So within data, the way you enter data is like C and then parenthesis, and within that you enter all the values. So 0 frequency 5 means 5 times zeros. So I can write 0, 0, 0, 0, 0, 5 times. And then I can write 1 9 times. But that is very tedious, like you have to type so many times. So there is an easier way. You can repeat. You can repeat using REP. So type REP, select, and say I want to repeat 0 5 times. And then put a comma, and then again say REP, select REP, and I want to repeat 1 9 times. Repeat 2 6 times. And then I'm going to hit comma and then go down. Otherwise, we'll not be able to see what we are typing. We'll repeat 3 4 times. And then last one, repeat 4. Actually on 1 time, so that's okay. So this is our data. If you run this, you can run this from anywhere. So now we have this data. If you want to check data, you can simply type data and run. And you notice this is what we have. 5 times 0, 9 times 1, and so on. With this data, find sample mean. So how do I find mean? Mean is mean of your data. So 1.48. So when you type mean and supply data, it will calculate mean. Standard deviation, SD. So if you do data, it calculates standard deviation 1.1. Construct a histogram. So let's go full screen, otherwise we will not be able to see histogram. Let me clean this up. HIST and data. So it creates this histogram. Find the first quartile. There is a function quantile. And we supply data and first quartile is 0.25. So 25th quartile is 1. And then it says median, third quartile. So you can do the same thing. In fact, it is easier if you do PROBS equals C and say I want 0.25, I want 0.5 for the median, 0.75 for the third quartile, so 0.4, 0.9. So you can get those numbers in one go. Construct a line graph of the data. So if you want to plot this data, you simply say plot. So my data is stored in data. So we run that line and it will plot whatever it has. It will just create a plot there. Last one, construct stem plot. So stem, STEM, and our data is data. So there are a lot of examples of stem plot in your book also. But how do we get it? So we will create, that plot just comes below here. So when you are working on the assignments, you can do by hand. If you are using writing by hand, that's okay, and take pictures and upload. Or if you are using a Word file, you can actually, any plot that you have here, you can copy and paste very easily. Like, for example, if you do export, and it says save image, you can save it, or copy it to the clipboard. You can copy from there and paste it in the Word file. So whatever you like to do. Before the test. Yeah. And I also sent you an email. So you can do it anytime in this week. And that should be no problem. Yeah. Let me close this so that. Okay.